Thank you. Okay, so just now I have talked about uh, how to find out the friction force, how to find out the acceleration of the mass center, the angular acceleration. We can apply equations of motions, right? When you apply equations of motions, never forget we have three scalar equations F equal to mag. We mean from the FBD, from the real force analysis, you have the resultant force, and then equal to mag, the kinetic force. Ag is actually the acceleration of the mass center. Also, we have sigma mg equal to ig alpha or sigma m any point, just for example, sigma mic equal to sigma mkic. So when you calculate sigma mic, it should be calculate the moment about the moment about the instantaneous center. And here it's very strange that when you take the IC, when you take the IC as a moment, when you take the IC as, to calculate the moment, from the real force system, you will find out actually there is no moment, right? Because vertical position, for vertical position and all the forces, okay, all the forces passing through the IC, okay, vertical position, all the forces passing through IC, okay, and so when you calculate the moment about IC, when you calculate the moment about IC again and again, when you calculate the moment about IC, the friction force passing through the IC, the normal force passing through the IC, and the rate passing through the IC, and the kinetic force passing through the IC. The moment from FBD about IC is equal to 0. And then we calculate the moment about IC from the KD. From the KD, that IG alpha also the AG will have the moment about IC, and you can find out your answer. Okay. Also, I can ask you to find out the friction force at the initial position, or the angular acceleration at the initial position, because at the initial state, even the disk is at rest, but definitely it got angular acceleration, and that's why it start to roll, right? How to calculate? You can apply equations of motion also. Okay. So it's time to determine the kinetic energy of the disk at this instant. Here we only have the you can draw FBD when no friction force is given, or here it's rolling without slipping. We say when it's rolling without slipping, the friction force did no work, right? Only the weight, only the spring force did work. They are all conservative forces, so the energy is conserved. Here we only need to determine the kinetic energy of the disk. It's rolling without sleeping, so the answer should be which one? It's given, the mass center, its velocity is given. So can you tell me the kinetic energy? The kinetic energy should have two parts, right? Translational kinetic energy plus rotational kinetic energy. Translational kinetic energy is this one, right? Kinetic energy is this one, right? Why? Because what? Because here it should be right Ig omega square, rotational kinetic energy. Omega is equal to the velocity of the mass center divided by its distance to IC, because rolling without sleeping, the contact point will be the IC. Okay, so this is 10. So the answer should be C. At the instant shown, the spring is undeformed. Determine the change in potential energy if the tangent cage disk rolls without slipping. Okay, again, it rolls without slipping. We need to find out the change in potential energy. Okay, so potential energy here include gravitational potential energy plus the elastic kinetic energy, right? The elastic potential energy. The spring is undeformed. At this instant, the is undeformed. And the instant show determine the change in potential energy. So it's undeformed. So it's V1 is equal to V1 K. K, this is for the elastic. Okay, we use elastic plus Vg, right? And V2 V2 equal to V2 elastic plus V2G, right? So you can calculate it by yourself, okay? So this one, you do before this, we just would like to give a brief introduction to the linear momentum, okay? Because I really like you to just have some, yes, we don't. So you need to know the definition of planar of the momentum. Okay, this is wait a minute. So chapter 19 is about the impulse and momentum. Impulse and momentum we have learned for a particle, but here is a rigid body because sometimes the time we need to figure out. So we need to use the principle of impulse and momentum. And first definition of linear and angular momentum. The linear momentum is still for a particle is equal to ma mv, right? Here, for a rigid body, the linear momentum is equal to mvg. Vg is the velocity of its mass center or gravity center. Okay, so here the linear momentum. So mvg. Okay, this linear momentum, and just like here, this is for rigid body. Its velocity of the mass center is this way. So we can decompose it into x component and y component. So the momentum linear momentum we can calculate. Again, the linear momentum is a vector, so we can use its x component, y component, okay? And except the linear momentum, we have the angular momentum. And so L to indicate the linear momentum, H indicates the angular momentum. Here, angular momentum, again, you need to define its moment center or the moment axis. Here, we only talk about the angular momentum about an axis, okay, or about G. G axis is actually perpendicular to the plane, okay. We talk about the momentum about the axis perpendicular to the plane or passing through G, okay. So the angular momentum and m will be replaced by the moment inertia, and the velocity will be replaced by the angular velocity, okay. So this will be the angular momentum. Here we have the body momentum diagram. So mvg, linear momentum, and ig omega is the angular momentum, okay. Angular momentum, and here so we just you need to just okay we memorize this or just you here you the derivation process. If you are interested, you can start it by yourself. Okay. And to show how to calculate the linear and angular momentum for rigid bodies, again, we need to know the motion of the rigid body. If it's translation, things will be easier. Because for translation and the linear momentum is equal to mass times the velocity of its mass center. And for translation, we know that the velocity of any point on this body will be equal with each other. So you can calculate the velocity of any point on this rigid body, and then you can use this to find out its linear momentum. For the angular momentum, we know angular momentum about here again and again. Angular momentum, you need to specify the moment center and is equal to Ig omega. Omega is angular velocity because it's translation. The angular velocity is equal to 0. So for pure translation, the angular momentum is equal to 0. Okay, so and for rotation about the fixed axis, according to the definition, the linear momentum is equal to mvg. Okay, so you need to find out the velocity of the gravity center, and vg is equal to rg omega, right? Because for a rigid body, which is rotating, any point on this rigid body will have a circular path, and the velocity will be perpendicular to the radius and will be equal to the distance to the rotation center times the angular velocity, right? So this is for linear momentum, and its angular momentum also we can calculate about the gravity center that's still equal to Ig omega. Yeah, again and again, you replace m with ig, vg with omega. Okay, and ig omega, according to what we have learned before, sometimes it will be convenient to compute the angular momentum of the body about the center of rotation O. So HO momentum will have two parts. The moment by the linear momentum and the angular momentum. Okay, so here the linear momentum you can just regard it as a force, and the angular momentum is the moment of a force. Okay, so the calculation is exactly follow the calculation of the angular momentum about any point actually follow the same rules of the moment by a force, right? Same rules. Okay, so and here mvg we know vg equal to rg omega. So again we have the ig plus mrg squared. We can apply parallel axis theorem. This one is actually the minus moment inertia about the rotation center. So we have ho equal to I omega. Okay, so the angular momentum here again and again, if you need to calculate the angular momentum, you just about any point, you can just have the momentum diagram. You can have the just like exactly you have the body momentum diagram, and then take the linear momentum as the force, angular momentum as the momentum over force. Okay, and then you can calculate the angular momentum about any point, just like the moment of force about any point. Okay, for the general motion, so it will have the linear momentum, angular momentum. If we need to calculate the angular momentum about any point, for example, point A, so just like here, this is just like a force, okay? This is just like M, right? And then if you need to calculate the moment about point A, what will be? It will equal to the m about g plus the force, the moment by the force about A, right? Here, what we say? Here it will be Ig omega, right? This is a force. Sorry, this is a moment about G, right? This one is uh, the moment by the linear momentum, right? Or you can just say this is the momentum of the force. Again, so sorry, it's not force. I mean, it's a vector. I just want you to calculate the angular momentum using what you have learned before in studies, how to calculate the moment by a force. You can just, they follow the same rules, the same calculation regulations. Okay, so hope you can follow me. Okay, and I can understand this. Okay, this is how to calculate the linear momentum and angular momentum. Just like here at a given instant, the 10 kg disc and 5 kg bar have the motion, so determine the angular momentum about point G and about point P for the disc, and about the G and about the IC for the bar and the instant. So for this, if you need to calculate the angular momentum, we need to, for the angular momentum, we know it's use H to indicate the angular momentum. For the angular momentum, we need to specify the moment center. This is about G. Angular momentum about point G is equal to Ig alpha, right? If you need to, oh, sorry, Ig omega, sorry, Ig omega. And omega is given, so we can find out Ig is given, okay? So we can find out the angular momentum about point G just directly. But about the point B, because we should know we have MAG, you should have IgM VG is the linear momentum, right? And linear momentum MVG and VG, how can we calculate VG? Because this is rotating, so VG should be perpendicular, right? And this VG. And so when you calculate the HB, it will have two parts, HG plus H B by the linear momentum. And this part is equal to the moment arm times mvg, right? Exactly just like you calculate the moment of a force, okay? And for this one, again, we know it's vg. Can you find out the vg? For the bar, for the AB, we know VA is downward, VB should go to the left, horizontal, and then draw the perpendicular line, right? Draw the perpendicular line, and this will be the IC. And then after you determine the IC, you can find out the velocity, right, of any point, because the velocity of any point should be perpendicular to the distance to IC. And then after you find out the VG, you can calculate the linear momentum and you can calculate the angular momentum. Okay, so for the linear momentum and the angular momentum is just a brief introduction. And for the principle of impulse and momentum, it will be exactly the same. The initial linear momentum plus the linear impulse. Linear impulse is the is to measure the effect of the forces over the time. Okay, so linear momentum plus linear impulse will equal to the final linear momentum. Okay, and linear momentum is calculated by its mass times the velocity of the mass center. And here, to calculate the linear impulse, you need to draw FBD, and then you need to integrate the force over time. If it's a constant, so it will equal to FT, right? And for the linear momentum, you should have initial momentum diagram and plus the FBD. This is a linear impulse diagram. It's just FBD, but you need to do integration and the final momentum integral. Okay. For the angular momentum, also the same. The initial angular momentum plus the angular impulse will equal to the final angular momentum. Okay, so we just have a brief introduction of chapter 19. And if you need the knowledge later on, you can study by yourself and you have the a little bit knowledge about it. Okay, so let's back to let's back to the conservation of energy or the principle of work and energy. Okay, let's continue the next part. Okay. Before we finish this, we have some work, some problem, just like here, attention quiz. Blocks A and B are released from rest and the disk turns 2 revolutions, okay? The V2 of the system includes a term for the V2, the potential energy of the system includes a term for if and the data line is given. And so if the block, the gravity center is in line with the data line, so the potential gravitational potential energy should be equal to 0, right? From the disk turns 2 revolutions. So this means this is sorry, this is, for example, this is 2 meter, okay? This is 1 meter. Here the initial is 2 meter. Well, the V2 of the system includes a term for which one? So anyhow, will include the disk? No, because when it rotates, the gravity center of the disk will be horizontal, will be in line with data line. So definitely no disk, right? So only the 2 blocks, okay. A standard bar is released from rest while in the horizontal position. The kinetic energy of the bar when it has rotated through 90 degrees is, yeah, this one you can figure out, okay? When it rotated, this is horizontal, and then should be this way, right? The kinetic energy of the bar is rotates. It's rotating. It's rotating, so its kinetic energy will equal to this one, this one, this one, or this one. Can you tell me your answer? Yeah, very good. D, yes. The when it's rotating and the kinetic energy still can be expressed in terms of the translation with the mass center plus rotation with the mass center. Definitely, if this is all, you can just express as right. Definitely, you can just do this way, okay? But here, IO is the mass moment inertia about with the rotation center, but you can express the kinetic energy using this, okay? Yeah, very good. Okay, so now let's back to the problem solving. A 50 pound bar is rotating downward at 2 radius per second. The spring has an outstretched length of 2 feet and a spring constant. The coefficient is given. We need to find the angle measured downward, down from the horizontal to which the bar rotates before it stops its initial downward movement. Initially, this bar is rotating with the angular velocity equal to 2 meters per second. And initially, the spring has a straight length. And then, after it rotates to some time, for some time, and AB will start to rotate, right? According to our daily experience, we need to find out the angle. We need to find out when it will start rotating. Why it will start rotating? For AB, you draw AB, you will find out only the weight and the spring force to works, right? So energy is conserved, right? And so energy is conserved, you can just find out the potential energy and kinetic energy. The potential energy at the initial position plus the kinetic energy at the initial position should equal to the the final potential energy plus final kinetic energy. I would like to ask you to do by a conservation of energy and principle of work and energy. I mean, two approaches. One is to apply conservation of energy. The other is to apply the principle of work and energy and then submit, okay? Okay, you need to do in two ways, okay? Okay, do you got it? Apply conservation of energy and apply principle of work and energy, and then submit online. And our final exam will be held next Saturday afternoon, 4 p.m. to 6 p.m. And it will include only include the kinetics. Okay, so that will be chapter 13 to 15 and chapter 17 to 18. Um, about chapter 19, the linear momentum, angular momentum, and I know it's